Welcome to the Explainer. Today, we're doing something really fun. We're going to break down a pretty major mathematical concept as if we were, say, 4 years old, just sitting on the playroom floor with a giant math treasure map and a big box of toys. We're talking about rectangular coordinate systems. Now, I know, that sounds like a big, intimidating grown-up term, but I promise you, it's literally just a brilliant way to figure out exactly where your toys are hiding. Okay, let's dive into this. We're going to see how a simple playroom map actually connects to something huge, calculus, which, by the way, is really just a big fancy word for tracking how our toys move, all starts right here on this very map. So imagine I hand you a map, but it's just a single straight line, kind of like a ruler, and I tell you, hey, the toy's at 5. Now, if we were on a straight track, that makes total sense. Think of a toy train on a straight track, or someone walking on a tightrope, or even just sliding your finger down a ruler. Those are 3 great examples of a simple, one-dimensional world. But what if we aren't on a tightrope? What if we're standing right in the middle of a huge flat playroom floor? If I say the toy is at 5, you'd immediately ask, 5 what? 5 steps right? 5 steps straight ahead? You know, the most common mistake people make here is thinking one number is enough for a big room. It's not. A single line completely fails in a 2-dimensional world, and this is absolutely crucial because in calculus, we aren't just tracking toy cars driving on straight, boring roads. We're tracking rockets flying through the giant open sky. We need a way better map. To solve this exact problem, mathematicians came up with something called analytic geometry. Simply put, analytic geometry is just math's clever way of playing with pictures and numbers at the exact same time. Think of it like giving a toy robot a special number tag, or turning a drawing of a triangle into a list of numbers, or even making a giant floor map entirely out of math. Those are 3 perfect examples of analytic geometry in action. A super common mistake is thinking that drawing shapes and counting numbers are 2 totally different games. They definitely aren't. This connection is exactly why it works so well. It gives pictures exact, precise numbers. And calculus absolutely relies on this trick, because calculus essentially watches how those picture numbers change shape over time. So the crucial point is how we actually build this big, flat floor map. We do it by taking 2 regular number lines and crossing them to make a giant plus sign right on the floor. First, we lay one number line flat, going left and right. We call this the x-axis. It's just like a toy car driving left and right across the carpet. Then we take a second number line and stand it straight up, going up and down. That's the y-axis, kind of like a toy airplane, flying straight up to the ceiling and down to the floor. Now, a big mistake here is accidentally putting the y-axis flat and standing the x-axis up. You definitely don't want to do that. To give you a sneak peek into calculus, the flat x-axis is usually time ticking forward, and the tall y-axis tells us how fast our toy is going. Now, every good treasure map absolutely needs a starting point, right? Since both of our number lines have their own 0, we cross them right at their exact zeros. That intersection is called the origin. For a quick visual intuition, just think of the origin as your starting home base. Waking up in your own bed, standing at the start line of a tricycle race, or pointing to the exact center of a giant pepperoni pizza, those are 3 awesome examples of starting right at home base. The absolute biggest mistake you can make is forgetting to start at home base and just starting your map wherever you feel like it. You must start at the origin. Calculus loves this spot, by the way. It calls home base the initial state, the very moment right before our toy rocket launches. Because one single number wasn't enough, we now use 2 numbers to find our toy. We call this an ordered pair. It's usually written like a little tag with 2 numbers inside parentheses. It works perfectly because the first number, x, tells you exactly how many steps to walk sideways, and the second number, y, tells you how many steps to walk up or down. Think of it like a set of game instructions. Walk 2 steps, then fly 3 steps. Or drive 4 steps, then dig down 1 step. Or maybe hop 1 step left, then jump 2 steps up. A really common mistake here is trying to do both moves at the exact same time diagonally. No way! It's sideways first, then up or down. These exact little pairs are the magic dots that calculus connects to see how things grow. But I've got to give you a massive warning right now. Order absolutely matters. Walking 3 steps right and 5 steps up is completely different from walking 5 steps left and 3 steps up. Putting a toy inside a box is totally different from putting a heavy box on top of a toy. Or putting your shoes on before your socks, that's just silly. If you mix up your X and Y numbers, you're not going to find your favorite teddy bear. You're going to end up in the closet with the dirty socks. The first number is always sideways, the second is always up and down. If you make this mistake in calculus and mix your numbers up, your math rocket literally crashes into the ground instead of going to space. What if you already have a toy sitting somewhere on the floor and you want to discover its secret numbers? Well, you use something called projection. Imagine holding a flashlight. If you shine a light straight down on a toy block, the shadow hits the flat x-axis to give you your x number. If you shine a light sideways on a doll, the shadow hits the tall y-axis for the y number. Shining a light on a puzzle piece to find where its shadow hits the wall is our third example. It works perfectly because shadows just don't lie. A common mistake here is shining the flashlight slanted instead of perfectly straight down. That totally ruins the secret number. In calculus, we actually use these exact shadow boundaries to figure out the area underneath a flying toy. Let's actually walk through 3 exact examples of moving from home base to find toys. First, let's find point P at 3, 2. Start at home base, walk 3 right, 2 up. Boom, found it. Next up, P at -2, 4. You'd walk 2 left, 4 up. And last, P at 4, -3. That's 4 right, 3 down. Visualizing this makes it so simple. Positives mean right or up, and negatives mean left or down. A big mistake kids make here is seeing a negative number and going the wrong way, like accidentally walking right when it says negative. We have to follow the instructions perfectly. When we map out lots of these points and track how fast they change from one toy to the next, we're actually doing a famous calculus trick called finding a derivative. Notice how crossing our 2 giant number lines divides the floor into 4 big rooms? We call these rooms quadrants. Just think of them like 4 bedrooms situated around our home base. Quadrant I is the sunshine room, where everything is positive. Quadrant 2 is the left side room, where we go left but still up. Quadrant 3 is like the basement, where everything is negative, left and down. And Quadrant 4 is the right side basement. This setup works perfectly to tell us exactly where a toy lives just by looking at its plus or minus signs. A common mistake is forgetting that walking left or down means negative, just like taking toys away. Calculus totally cares about these rooms to quickly know if a toy's speed is increasing in the positive rooms or decreasing in the negative ones. Now, what's really interesting about this next part is what happens if we don't take any steps in a certain direction? What if one of the numbers is a big fat 0? Well, the toy isn't hiding inside a room at all. It's sitting directly on the line. For 5, 0, you walk 5 right, but 0 steps up. You are right on the x-axis line. For 0, -3, that's 0 sideways, 3 down. You're right on the y-axis. And 0, 0, you are sitting directly on the origin right at home base. The biggest mistake kids make here is getting confused and walking sideways when they see a 0 for x. 0 means stop. In calculus, hitting these 0 lines tells us exactly when a flying toy finally hits the ground. This brings us to a seriously awesome secret. Every single toy on this map has a secret password, the numbers. And every secret password matches exactly 1 toy. It's a flawless, perfect match. If the red car is at 1, 1 and the blue block is at 2, 2, then the password 1, 1 will always take you exactly to the red car. It works wonderfully to connect algebra right back to geometry. A common mistake is thinking 2 toys can have the exact same spot without crashing into each other. Every point is completely unique. Because every point is a perfect match, calculus uses these exact passwords to perfectly predict where a toy will be tomorrow. Okay, let's play a game. Say 2 kids are on the map and they want to meet exactly in the middle to share a toy. We use something called the midpoint theorem. To find the middle, all you really have to do is find the average. Sliding halfway up a slide, digging halfway across a sandbox, or breaking a cookie perfectly halfway in 2 to share, these are 3 great examples of finding a midpoint. It works because finding the average balances the distance perfectly between the 2. A common mistake here is trying to subtract the numbers instead of adding them up to share. Just add them and divide by 2. Averaging 2 spots to find the middle is actually the very first baby step to finding average velocity in calculus. What's truly amazing is that finding the midpoint in this huge 2D room isn't scary at all. It's honestly just 2 simple counting games played at the exact same time. Finding the middle of a flat line is just averaging 2 numbers. So in our playroom, we just do that exact same baby math twice. Once for the sideways numbers and once for the up and down numbers. A huge common mistake is trying to mix the sideways x numbers and the up-down y numbers together in a big soup when you're averaging them. Keep them separate. X with x, y with y. Calculus loves this trick of breaking big, scary 2D problems into tiny, simple baby steps. Let's run through 3 fast examples so you can see just how easy this is. Think of it like sharing cookies. Kid A has 2 cookies, Kid B has 8 cookies, they meet in the middle with 5. Kid A has 4, B has 10, they meet with 7. So point 2, 4, and 8, 10 meet right at 5, 7. Easy, right? If one kid is at home base 0, 0, and the other is at 6, 8, well, half of 6 is 3, half of 8 is 4. They meet at 3, 4. Even with negative numbers, negative 4 and 8 makes 4, cut in half is 2. The mistake to watch out for here is simply forgetting to divide by 2 at the very end to share. Calculus uses this exact averaging trick all the time to find precise midpoints for drawing tangent lines. Let's move on and see how this all builds, because here comes the coolest part. If we use an equation like y equals x squared, we can generate endless points. A jump rope curving down to the floor, a beautiful rainbow curving up into the sky, or the path of a bouncy ball flying across the rim. When you put hundreds of these dots on our map really close together, they line up to create smooth, swooping shapes and curves. It works because math is really just a connected path of toys. A common mistake kids make is connecting the dots with sharp, jagged straight lines when it's actually supposed to be a smooth, swoopy curve. Calculus is basically the ultimate magnifying glass that zooms in on these exact curves to see just how curvy they really are. When we zoom out, we get to see this incredible evolution of play. First, we were just counting single numbers on our fingers. Then, we learned how to walk left and right on a flat map. Finally, we learned how to draw smooth, swooping curves across the whole playroom. We literally went from basic counting to coordinates to equations and finally to curves. It's a whole journey. The big mistake people make is thinking calculus is some scary monster that just comes out of nowhere. It doesn't. It naturally grows right out of these basic playroom games. Every single dot and line builds the ultimate groundwork for studying the universe. Which brings us to the end of our treasure map journey, but the very beginning of a much bigger one. Because once mathematics has this map perfectly laid out on the floor, we can start asking the most epic questions. If this swooping curve is a toy rocket flying to Mars, how steep is its path right now? Room! If it keeps going, exactly where is it going to land? Zoom! Those are the amazing questions that derivatives and calculus answer. And you now know the secret treasure map it all starts with. So what math curve are you going to draw next?